Okay, let's jump right into this explainer. We're going to completely demystify the incredibly rigorous, granular systems engineering approach required to design life-saving drones for natural disasters. When a flood hits, we see a drone up there and just think, oh, what a handy tool. But the reality? The exact, precise math, the operational logic, and the structural engineering required just to get that drone in the air flawlessly and on time, it's absolutely staggering how extremely detailed it has to be. We've got 6 key areas to tackle today. We'll start with the systems engineering framework, move into defining the disaster mission, and decoding needs into requirements. Then we'll hit the DORI standard, the math of aerial surveillance, and finally, wrap up with functional system decomposition. Section 1. The Systems Engineering Framework. Macro-level logic. So here's the crucial thing. Systems engineering isn't just about building a drone. No. It's a top-down, iterative process that engineers the entire life cycle of a product to guarantee it meets exact user needs. It's about looking at the complete problem with excruciating precision. We're talking business analysis, the technical needs of the operator, maintenance, even how you dispose of it at the end. It ensures we aren't just building a system right, but that we're actually building the right system. Now, within this framework, you have this really important macro separation of duties. On one hand, you have the ConOps, or concept of operations. That defines what the leadership, say the disaster agency writing the checks, strategically assumes will happen. But then you have the OpsCon, the operational concept. This is the rigorous, user-oriented side that describes exactly what the physical drone system will do from the perspective of the operator on the ground. You literally have to separate these. Otherwise, visionary, pie-in-the-sky goals completely obscure the physical realities. Section 2. Defining the disaster mission. Chaos versus structure. Picture this. The landscape is completely submerged. Total chaos. When the local disaster management authority needs to deploy an aerial system to assess just 1 square kilometer of this flood, their demands are intensely specific. They expect the system to be stored locally in an unconditioned warehouse, chucked into the back of a local vehicle, and ready to launch in under an hour. Oh, and it has to operate seamlessly in a drizzle, run by a completely unskilled volunteer. Section 3. Decoding needs into requirements. The engineering translation. So how do you actually build that? A stakeholder will tell you they just need to find survivors. Right, that's a capability. But a systems engineer has to translate that into structured, highly detailed, quantifiable statements. Requirements like the system shall cover a 1 square kilometer area, or the system shall detect humans. Notice the word shall there? A requirement has to be mathematically validated during testing. You can't just say, make it see well. You have to define exactly what seeing well means using math. And we have to get unbelievably granular here. Detecting a human isn't a monolith. A camera angle perfectly calibrated to spot someone standing up might completely miss a survivor sitting on a cot surrounded by floodwaters. The engineering requirements must explicitly encompass all these different physical postures. Section 4. The DORI standard. Pixels and precision. To hit those requirements, we rely on the DORI standard. First up is detection, at a baseline of 25 pixels per meter. At this resolution, the operator can just barely determine that there is a human presence on the ground. It really just answers a simple yes or no, is someone down there, but honestly, you can't tell much else. Step that up to 62 pixels per meter, and we get observation. This is a huge threshold. Characteristic details, like the specific color of someone's clothing, finally start to come into view. Think about it. If rescue teams are looking for a missing person reported to be wearing a red shirt, this is the absolute minimum mathematical requirement for your camera. Then clarity drastically improves at the recognition tier. That's 125 pixels per meter. Now operators have a high degree of certainty about who or what they're looking at. If conditions are decent, you can even begin to make out larger text, like a license plate on a stranded vehicle. Finally, at an incredibly dense 250 pixels per meter, we achieve identification. This gives you undeniable clarity. You can positively identify a person beyond a reasonable doubt. But to achieve this extreme level of detail from a moving drone during a disaster, you have to perfectly, mathematically match the camera sensor to the exact flight altitude. Section 5. The math of aerial surveillance. Trigonometry in the sky. That brings us to the actual math. This seemingly simple formula is absolutely vital. It calculates the camera's footprint on the ground. That's the base, b. You find it by taking 2, multiplying it by the drone's flight height, h, and then multiplying that by the tangent of half the camera lens's exact angle of view, theta. Basically, this tells the system engineer exactly how wide of an area a single picture covers, which then dictates exactly how many pictures you need to cover that required 1 square kilometer. Let's look at how this math impacts reality because it is hyper-precise. To scan a 1 kilometer area, you have to fly in a sweeping grid pattern. Let's say you fly at a height of 50 meters with a 10% image overlap. The drone has to travel 29,000 meters. To do that on a 45-minute battery, it needs to fly at 10.7 meters per second. But if you double that height to 100 meters, your camera sees way more at once. The total flight distance plummets to 16,000 meters, and the drone can fly a lot slower, at 5.9 meters per second. But wait, you have to factor in operational overlap. A sudden gust of wind means the drone tilts, and boom, you missed a frame. Bumping that overlap to 20% to be safe means the drone now has to fly further and faster to finish before the battery dies. Literally everything is a meticulously balanced, extremely detailed mathematical trade-off.
Section 6. Functional System Decomposition, Cradle to Grave.
This step-by-step breakdown proves that systems engineering really does cover the entire life cycle. It starts at step 1 with the literal input of the initial deployment order and identifying how to transport the gear. Then it moves through a local readiness check, the physical transport, on-site setup, flying the actual mission, and it doesn't end until the equipment is safely packed away back in that local unconditioned storage unit. Every single one of these steps has strictly defined inputs and outputs that engineers must rigorously account for.
Which leaves us with this final, provocative thought to take away from this explainer. The systems engineering lifecycle ensures we have accounted for literally every pixel, every meter per second of wind, every single battery constraint. We can engineer the perfect mathematical system on paper, but the ultimate engineering challenge isn't just perfecting the math in a lab, is it? It's designing a highly sophisticated interface that ensures this extremely complex system remains perfectly usable by a stressed, untrained volunteer when the reality on the ground is terrifyingly chaotic. Because in disaster relief, all that extreme mathematical detail only matters if it actually saves a life.